Yeah, so today we're going to learn about double integral. Like what is the use of double integral and what is this thing basically. So like I intend to explain like how this thing works and what does it mean really, right? So like instead of just solving all the math problems, if we can visualize what double integral actually is and how it evaluates, that will give us a better understanding of the whole concept, right? So first, when we open our math books or papers, we will get some problems like this in double integrals. So like this problem here, it says evaluate this function x cube y square minus 2x square y cube dA, where d is bound by y equals to x plus 1, x minus 3, y equals to minus x square. So first thing that we see here, there is a function and that is bound by a domain, and that domain has two equations, right? So for x and y axes. So first thing that we need to understand here, this dA part that we are seeing, right? So this dA part is basically a multiple of dx and dy, right? So we are doing double integrals when there are multiple variables, right? So double integral is when there is like two variables like f of x, y, right? So when like this things happen, right? So in your exam books and all, you will see that there is something written as fxy in parentheses, but here we have to write it like this for the convention. So we'll get some function first, and that function will have like two variables inside it, so the integration will also be evaluated in those orders, right? So if you do a differentiation of this function, right, you will get something like when we'll do differentiation by parts, you will get like dx part and you will get a dy part, right? So when we are trying to revert that, so that time we are getting a function that is a multiple of both of those things here. So it's written as dA, that denotes basically dx dot dy, right? So not to worry about it too much. Now let's try to solve it. So first thing is we need to understand the domain. So what we are getting from this information here is y has two equations, so x plus 1 into x minus 3, and another is minus x square. So with these two equations, we have to find the limits, like lower limits and upper limits of both x and y. So let's try to solve that thing. So basically this means that we need to solve this equation that is forming by substituting the value of y. So the equation will be something like this: x plus 1, x minus 3, this is equals to minus x square, right? So this is our equation, but we want to solve it. So here we need to solve it like this. So this is Mathematica, by the way. So here we need to solve it like this, put it in square brackets, and then we'll just say solve, and that should do it. It will give us the results. Yeah, so as you can see, we got our roots, right? We got our roots, like x belongs from the lower limit of x seems to be 1 minus root 7 by 2, and upper limit will be 1 plus root 7 by 2. That's fine. And if we put this in this equation, one of these equations, right, we put this values in one of these equation, then we'll get the y limits as well. We don't need that actually right now, at least. So next thing what we have to do is we need to visualize, we need to plot it so that we get the better understanding of the domain, right? So first we will plot it in 2D, because this domain seems to be in only in 2 dimensions basically. So we'll use this plot function, right? So we'll use this plot function, and it will basically we'll have to provide two of the functions of y, right, that we have above. So we'll write it x plus 1 multiplied by x minus 3, and another equation that we have says y equals to minus x square, so that we will also put that. And next what we have to do is give it a range, right? How far we need to put the values of x. like what we want to plot here basically. So I will take the values. So if I put -1 in the equation, right, so y becomes 0. So I will put the lower limit as -1 and upper limit put like 3 or something. Yeah, now let's see. So okay, we got our graph and it kind of looks like a fish, but if you see this graph carefully, you'll see that the x ranges from minus somewhere around -1 to close to 2 here, right? So somewhere around -1 to this, close to this 2 value, the x ranges from this points, right? So that means, and we have the intersection in here as well, so that means two of the roots of the equations are in here. So we can reduce the range of this graph to 2 here. Yeah, so that gives a nearer picture of the graph. Okay, so now that we have found our domain plot, right, so that means this is the domain where all the values of the function belongs, right? So what that means, so we'll see what that means. So now we'll move on to the next part. So we have found our roots, we have plotted our domain. Now we'll see the equation and the function itself. So we have this function x cube y square minus 2x square y cube. Okay, so we'll write it first. So let me write the function. So if we want to write in a generic form, we will have to write like this by convention. So now the function is, okay, so I need to move up a bit. So x cube y square, so function is x cube multiplied by y square minus x cube multiplied by y square minus 2x square y cube minus 2x square, it's not 22, x square y cube, right? I think this is correct, x cube y square. And what I can do is I can also print it once so that validates. So x cube y square minus 2x square y cube, x cube y square minus 2x square y cube. Yeah, that's fine, that's our function, right? So now what we want to do is we want to plot this function itself. So we'll put in our x ranges and y ranges, and then we'll see how does it look actually. So now something to think about, right? So what we are seeing here, this function, right? So this function is basically it depends on both of these variable x and y, right? And it gives another output, right? So that means we basically, including this function, if we think of this function as another variable, so then including this function we have in total 3 variables in this whole thing, right? So first we have this fxy, that is acting like a z variable here, and then we have x and y, right? So that means we have to plot it in a 3-dimensional space so that we can see how the function looks, right? So now what we are going to do is plot it in 3D. So this function is so this, what you are seeing here, x cube y square minus 2x square y cube, is a function of x and y. So now we have to plot it along with x and y and z axis, and that will be something like this: fx comma y, and then we have ranges like x I will take as same as before, -1 or 2, and now y, what should be the y ranges, right? You can see from here, right? So y is never crossing the origin, right? Y is not crossing the origin, that means the value is yeah. So and here also in below also you can see that after around like -4 it has moved upwards again. So the main solution part of that domain, that belongs somewhere in here, so that range you need to put. So I will put around bit liberally -5 to 2, right? And this is just some theming. I like this theme basically. So yeah, now we have plotted our function. So this is how our function looks in 3D, right? So now if you look carefully, it looks kind of like so when in math papers you see something like this, right? It doesn't make any sense, right? It doesn't make any sense. We just have to follow the rules of integration and solve it and get marks, right? But if you plot it and see, then it starts making sense, right? Because if you see this graph here, it kind of looks like some hilly area, right? It kind of looks like some some terrain in the wild, so some hilly area. And now we have to further make sense of our problem here. So that is this function currently is not mapped inside a domain, right? Like we have given ranges for the graph itself. So this ranges, you are not supposed to be confused with this, right? So this range that you are seeing here, that is the graph range, that's not the domain range, right? That is not domain range. So domain range will belong from the roots of the equations that we have solved here, right? And from lower limit to upper limit for both x and y, right? So currently the graph is showing like this, but the function is out in the open. So this is not what we want. Basically we need to plot this within the domain itself, then we will get what is mentioned in our problem. So to do that, what I'm going to do, I will copy it, I will let it be there for reference, and I'll do something else as well. So what I'm going to do, we need to basically, so this part I will keep it as it is, right? But this is the theme area, so you can totally ignore this. Even if you don't write it, nothing will happen. So now what we basically need to do is define the region of this function. So how we do that here is simply by calling region function. So region function, and inside that basically we need to write our own function, and that will, like, we have to define our own function with all the attributes mentioned in here. So we have three axes, x, y, and z. So g is basically our function itself, and then we need to provide it a range that is y as a function of x, right? So now we need to provide the range of y within its lower limit and upper limit, right? So now if you see this in this graph, right, then you can see the lower limit of the y equation is defined by this blue line, right? So by default the first one will take blue color and the second one will take yellow color. So that means this first equation of y, that is represented by blue color, and the second one is represented by yellow color. So the minimum of y, right, minus, like around something like -4. So this is met by this blue line, and the maximum of y, that is in here, right, that is here, that is inside this yellow line. So that means this line. So we can conclude that y that we have here, so y has a range, right? So y has a range from this one, x plus 1, first equation is -3, and the second equation, that is minus x square, right? So this is what is the range of y, and now we are going to restrict this function within this domain. Let's print it. Okay, got some error it seems. Okay, I'm missing a comma here. Yeah, got it. Okay, so now interesting thing, right? Interesting thing, can see this, we started from here, right? I told this function is not bound by anything, right? We have just plotted the function along x, y, z axis, and we have given a range for the graph, right? Now this function is bound within the range, within the domain range that is provided, right? Now it's starting to make sense, right? But what we are planning to do here seems to be something different than this reality. So if we think of this part of a mountain or hill or something of terrain, then the x-axis and y-axis are representing like length and width, right? And then this z-axis is representing our height, right? So that means what we are basically trying here is to calculate the volume of this function, and by that function we mean this part of this terrain, we mean part of this hilly area that we are seeing here. So to better visualize it in that manner, what we can write here is this thing. We can add a filling, right? Yeah, now it looks better. So basically what we are trying here is to calculate the volume of this area of this mountain range or whatever, or this part of this terrain. And if you see it in 2D, right, if I can move it, yeah, so it's hard to move it, but I'm trying to make sense of it. So if you can see, I have moved it along axes so that we are perpendicular to the z-axis, so to the x-axis. So you can see this is same as the domain graph, right? This is same as the domain graph. So that means the domain represents the area, and what now we have done is we have plotted the z-axis that is represented by the function, and now it gives us the total volume of that area. Now we are almost done. So basically this is what the double integration will achieve, right? Now if you actually want to do an integration, as we are in this find tool, it will give us easy way to solve the double integration. So we'll put the function here, and now we have to put the range, that actual range, like lower limit and upper limit of the solution that we found earlier, right? So we have to put this. So we'll copy this. This is the lower limit, right? So we'll copy this, put it in xmean. We'll copy this upper limit of x, we'll put it in xmax, sorry, and then for y we don't need to calculate the value actually. So we know that y is a function, right, of x, and y is a function of x. So we'll just write the lower limit equation here. What was it? x1, x plus 1 multiplied by x minus 3, and the upper limit was represented by minus x square, right? Rest of the variables we don't need here, right? And now this should give us the integration value. And in case you want the numerical value of this, just copy it, paste it in here, to roots. Okay, I pasted. Okay, didn't copy, is it? Okay, paste it in here. Yeah, so this is in whatever square meter or cubic meter or something, so this is the total volume of the function that we have seen, right? This hilly area, this part of this hilly area, right? This will be like 201 cubic meter if we think of it as in meter scale, right? So this is the use of double integral, and this is how to visualize it. So you plot the domain like this, you plot the function, and then you merge them together. So that will give you exactly what you want, and it makes things interesting as well, right? So there you go, that is double integral.